Hello, I'm DongJun from Korea University. Today, I'm here to present read-only prompt optimization for vision language few-shot learning. First, let me talk about the background of our research. In real world, fine-tuning large-scale vision language models such as CLIP to specific domains with limited training data is a crucial problem. Furthermore, the generalization capacity of pre-trained vision language models is usually compromised after fine-tuning, especially in data-deficient settings. For instance, as demonstrated in this table, domain generalization is severely compromised after the fine-tuning based on a linear probe. From now on, I'm going to explain our motivation. I trained co-op and co-co-op, which are the recent prompt learning methods, and linear probe, with 10 different few-shot sample training data. As shown in the figure upper left, the linear probe results in remarkably smaller performance variance compared to prompt learning methods. We conjecture that the high variance of prompt learning methods is due to internal representation shift induced by learnable prompts as illustrated in the figure bottom left, where randomly initialized prompts may negatively affect model adaptation in data-deficient settings. However, prompt learning method without the internal representation shift has not been explored yet. To sum up, we can summarize pros and cons of conventional prompt learning and linear probe as described in the figure left. Taking into consideration the pros and cons of the two methods, we conjecture that by integrating these two approaches, better generalization, parameter efficiency, and resolution of the variance issues could be achieved. Consequently, this led to the proposition of RPO, or read-only prompt optimization. In this section, I will explain how RPO works. This figure shows overview of RPO. I'd like to note that the only trainable part is the prompts, which are indicated with fire emoji, which shows the parameter efficiency of RPO. RPO consists of three main components listed below. First, read-only mechanism is implemented by the masked attention. We define read-only mask for visual encoder and text encoder, thereby blocking attention flow from learnable prompts to data tokens. By doing so, learnable prompts do not affect pre-trained feature space, thereby preventing internal representation shift, and learnable prompts only read and combine useful information from the pre-trained feature space through attention mechanism. The second component is the special token-based initialization, which can be improved convergence to more robust parameters. We initialize read-only prompts based on embeddings of the special tokens such as CLS token or EOS token. We add Gaussian noise to special token embedding to prevent constant initialization. Finally, to compute image-text similarity score, we compute similarity using a pair of visual prompt feature and text prompt feature. Given that the number of prompts is k, we compute k similarity scores and average them to compute final similarity score. It can be understood as ensembling k-separate classifiers without heavy computational overhead, thereby achieving better robustness. Through experiments, we aim to address the following three questions. For the first, in base to new generalization, RPO shows remarkable improvement in the majority of the benchmarks. Also, in domain generalization, RPO shows better domain generalization compared to baselines on 4 out of 5 benchmarks. In this analysis about the variance, we randomly sampled 10 few-shot training sets and trained RPO and co-op for 10 times. As shown in this figure, RPO shows remarkably smaller variance in every shot, as well as better performance. As a conclusion, parameter efficiency, generalization, and robustness to limited training data should be addressed as critical considerations in the perspective of large-scale vision language model adaptation. Also, continual learning and knowledge transfer have to be further explored within the context of read-only prompt optimization. Codes are available at our GitHub page. Thank you.